Hi, I'm going to do the Edrolo video because it wasn't really complete. So I'll read it out to you and we'll see. It's not going to be pretty, this, but anyway, be better than nothing. So a student uses a butane gas stove. So butane is C4 but, H double it plus 2, 10. Gas stove to heat a mug containing 40 mils of water. Okay, this amount of water we need to have as a mass. So 1 gram of water equals 1 mil. As far as we're concerned at the moment, we'll look at the density of water later. So if you've got 40 mils of water, we're going to have 40 grams of water. Okay, so this water was initially at 15 degrees, was allowed to burn until the water reached 49 degrees, so it's gone up a certain amount. Before the heating process, the butane, the fuel, had this mass, and then after it, it had this mass. This is a lower mass. 0.59 is lower than 0.80, which means that it's lost some mass because the fuel has turned into carbon dioxide and water when it's burnt. Assuming all the heat from the burning butane was captured by the water, so if the stove's just sitting underneath the water, it's all going to be, most of it will be lost, but we're assuming that all of the heat from the burning, so all of the energy has gone into the water. Calculate the heat of combustion of the butane in kilojoules per mole, as it would be written on a balanced equation. Alright, so if it's written on a balanced equation, we call the heat of combustion the change in enthalpy, and so we're going to have this change in enthalpy in kilojoules per mole. If we attach it with a balanced equation, then we call that a thermochemical equation, when this is attached to the balanced equation. So we might do that first. So we'll write a balanced equation for butane. So butane is C4 H10, and it's a gas. First 4 are gases, and then they become liquids. And we're always reacting it with oxygen, which is a gas, and you're making a certain amount of carbon dioxide if it's a complete combustion, and a certain amount of water. Water will be in the liquid state. That noise is my dog. She's a bit sick at the moment. Alright, and we're going to have a change in H at the end of this in kilojoules per mole. So we need to work out how much energy is going to be released. And remember, when you do this, this always needs to be negative. Edrolo, when they're doing this, because it's an exothermic reaction, it's releasing heat. Then change in H is the enthalpy in the products minus the enthalpy in the reactants, which means that you start with a certain amount of energy in your reactants and you end up with a certain amount of energy in your products. This number is a lower number than that number, so if that's a smaller number than this is larger. When you take it away, you'll end up with a negative value. Okay, so do not forget that negative. So we're going to have energy released. Need to do activation energy released, and we're working out the change in H, change in energy enthalpy. Right, so we need a balanced reaction. We've got 4 carbons here. Each carbon dioxide has 1 carbon, so we need 4 carbon dioxides. We've got 10 hydrogens, so we're doing the carbons first, then the hydrogens. The reason we're doing that is because there's 2 oxygens on this side and there's only 1 on that side. So if we work out how many oxygens we've got all together here, then we can just easily work out this number here. So we've got 10 hydrogens on here. They come in 2s on a water molecule, so we need 5 of those. Altogether we've got 4 lots of 2 and 5 lots of 1. So we've got 8 plus 5, so we've got 13 oxygens. Alright, they come in 2s over here, so you can't divide 13 by 2 evenly, which means we need to double everything. So instead of having 1 butane molecule, we will have 2, which will give us 8 carbon dioxide, 10 water molecules, which eventually will give us 26 oxygen, and then we can divide that in 2. Okay, so remember even numbered ones, 2, 4, 6, 8. For alkanes, you have to double the whole thing, which means that the kilojoules per mole is going to be for 2 moles. Alright, so we need to work out how much energy is coming from the butane in kilojoules per mole. So we've got 2 things we need to work out, the kilojoules and how many moles. So what we're doing is heating a cup of water. So we've got our water, and we have 40 mils of water. So the mass of water, because a mil is a gram at this point in time that we're looking at, the density, then we will say that we've got 40 grams of water. So this is the water. And we have butane in a stove, so butane, let's see, 4H10, and we have lit a flame. So we started with an initial mass of our butane, and we started with 43.80 grams, and then it went down to 43.59 grams. So we have used up and turned into a gas. Okay, so the mass has gone down because all of that has been turned into water and carbon dioxide and left as a gas. The reason that we have to do this as a liquid is, I won't discuss it at the moment. So the weight has gone down. Alright, so it's gone down, so we've used up 0.21 grams. So how much energy do you get for 0.21 grams of butane? The assumption is that all of that energy has been put into the water and heated the water up. So the water started at 15 degrees and it went up to it went up to 49 degrees. So the temperature rise, if we work out the temperature rise, it's 34 degrees. So we have heated the water by 34 degrees. Okay, so the difference between those two values. So what does that mean? How much energy is 34 degrees? So we know we're using this equation, Q equals MC change in temp. We're using the specific heat capacity of water. So specific heat capacity of water is how many joules of energy does it take for 1 gram of water to go up by 1 degree. So it takes 4.18 joules for 1 gram of water to go up 1 degree. So we need to know, if we've got 40 grams of water, then we have 40 times that. Okay, 40 lots of 4.18. Okay, so we would multiply that and we get 40 times. We want to have it not go 40 grams of water go up by 1 degree. We want 40 grams of water to go up 34 degrees. So we'll need 34 lots of that, 34 times that. So when you multiply those, the degrees cancel out, the grams cancel out, and you'll get your answer in joules. Okay, so if you multiply all of that, you'll get 5,684.80 joules on your calculator. How many of those numbers are useful? We need to start writing down significant figures. So we have significant figures. This is 3 numbers. Remember, every time, as soon as you hit a number at the beginning, every number after that, including zeros that are written, are significant. So if you're given 3 numbers like that, then we have 3 significant figures. Here, that was, I've written this incorrectly. This had 3 significant figures as well. And this is 3, this is 4. So if you've got more significant figures, then you use the least number when you're multiplying. Alright, so we're going to cut this down eventually to 3, but I might just convert it into kilojoules first, because we need to have our units as kilojoules and we've got it as joules. So when you're converting something, remember what you want is kilojoules, and what you've got are 5,684.80 joules, and we know that there is 1 kilojoule for 1,000 joules. So you're going to divide, when you take this over the other side and multiply, the number of kilojoules is going to be divided by 1,000. And 4.80, so joules, they'll cancel, and we'll get, if this is divided by 1,000, that's 1, 2, 3, so 5.684 kilojoules, and we need that as 3 significant figures, so it'll be 5.6, this is 4, so this rounds down to 8 kilojoules. Okay, so all of that I should have just had for the amount of energy up here. So we've got 5.68 kilojoules that's been trapped into here, and this 5.68 kilojoules came from combusting 0.21 grams of butane. So how much would you get if you had a gram? So if we divided this by this, we could get it for 1 gram. But we want to know how much you would get for a mole. So there's various points where you can turn this into moles. So we may as well turn this into moles now. So to turn it into moles, the number of moles of butane, if you've got the mass of butane, we need to know the molar mass. So we've got 0.21 grams of butane. The molar mass, we've got 4 lots of carbons 12. If you look on the periodic table, the molar mass of hydrogen is 1 gram per mole. So 4 lots of 12 is 48, 10 ones are 10, so we've got 58 grams that you need to have 1 mole of butane. And we've got 0.2 grams, so clearly we've got nowhere near a mole. So if you divide this by this in your calculator, you get 0.00326. No. Oh, I've done the classic thing here. This is a classic mistake. You're reading your numbers and you swap them around. Just be careful, there's always somebody in the class who does that every year. It's a bit of dyslexia, I think. So I copied my numbers wrong from my sheet. Be careful you don't do that. Alright, so that's how many moles we've burnt. A lot less than 1. So clearly, when we work out, we want to know how many kilojoules we will get for 1 mole. Or do we want to know for 1 mole? Do we want to know for 1 mole? We don't really want to know for 1 mole, do we? Where did I put this? We want to know for 2 moles. Alright, so when we set up our ratio, what we want is to know the number of kilojoules for 2 moles, because we're putting on our thermochemical equation, and we have worked out that we get 5.68 kilojoules. When you're doing calculations, you can keep all the numbers and then cut it down at the end. So you write your 3 significant figures, but keep all the numbers in the calculator. Alright, so 5.684 kilojoules for this many moles of butane. So the number of kilojoules for, remember, this is our ratio. Take it over the other side and multiply it, and the units will cancel out. So 2 moles. So we get, I'm not sure it worked it out. Oh, it was on Edrolo. It's alright, I shall find it. So we get 3,140 kilojoules. Another way of writing that is 3.14 by 10 to the 123 kilojoules. Okay, so if we write that on our thermochemical equation, turn this into a thermochemical equation, it'd be 3.14 by 10 to the 3 kilojoules per mole. That's how much you get for 2 moles. So this kilojoules per mole, remember, is not per 1 mole when it's written on a thermochemical equation.